And let's go very quick to Nima's presentation. I think we have about 20 minutes. Trisha, I already have one question for you, but let's wait to see if we have any time at the end of the presentation so we get to the questions. And Nima, while you're uploading, I'm going to give you a quick introduction. Dr. Nima Kargah-Ostadi has over 10 years of experience in transportation infrastructure management, applied statistics, data science, machine learning, and evolutionary computation. He has collaborated with FHWA and multiple state highway agencies in integrating their latest proven research in practice to improve their data-driven decision process. He is a member of ASCE Highway Pavements Committee and the TRB Pavement Management Systems Committee. He holds a PhD in civil engineering and a doctoral minor in computational science from Penn State University. He's a registered professional engineer and a certified project management professional. That being said, Nima, you have about 20 minutes. Please go ahead.
Thank you very much, Salar. Can you see my presentation?
I can see that, yes.
Okay, very good. Thank you for that introduction, and thanks to Penn State people who organized this conference for inviting me to this presentation. So I'm gonna just get started on this. Trisha and Matt talked about some of the innovations that have been implemented at state highway agencies. I'm going to talk a little bit about the future, a little bit about the state of the art, mostly on the emerging technologies, the most recent research on data collection and pre-processing, and also, of course, on data analysis and for data-driven decision-making. And then at the end, I'm going to talk a little bit about technology transfer from the state of the art into the state of the practice. I'm going to talk about technology readiness levels and technology transfer avenues. Well, as you saw in the presentations in this session, and of course in other sessions at this conference and any other conferences, we are seeing an evolving ecosystem of asset data. We are seeing digital twins and building information models in terms of the asset composition. And in terms of asset monitoring, condition monitoring, we are seeing a move from temporally discrete data sources to continuous streams of big data coming from Internet of Things and connected vehicles and edge devices. Along with the same change in the ecosystem, we are seeing a growing number of asset data types. While traditionally we had structured data, which were mostly measurements from sensors that were managed in a data warehouse, like a relational database, now we are moving into semi-structured and unstructured data sources that require more innovative methods for managing the data. So first, I'm going to talk a little bit about the data collection and pre-processing. Most of you guys who are in this session are familiar with deep learning and transfer learning technologies that are being used for extracting asset information, like asset inventory and maybe the condition of the asset. There's been a lot of research ongoing on these. There are some links throughout this presentation that you can go to and study a little bit more about that. But I'm going to talk more about the most emerging research about big data for asset inventory and condition, and a little bit about natural language processing. So big data is all about the distribution. Really, what's happening is that we have all this data coming from many different sources, and it is mainly big because of the speed of data generation. I mean, of course, there's other reasons for it to be big, like, LiDAR point clouds take up a lot of space. But really, the main issue here is the distribution of data that is coming and then how it is going to be processed. So we can learn a lot from other industries and even within the transportation industry, from transportation systems management and operations folks who have done a lot of work in this, in managing the big data with the new technologies that are available. One of the sources could be connected vehicle data. One of the emerging research that we see a lot happening is on using this crowdsourced, edge processed sensor data from the vehicles to extract the asset inventory and also do an assessment of the condition of the assets that are on the highways. So you can see some of these are from fleet of maintenance vehicles, which can be better calibrated. They all belong to the same organization. And some of them are just crowdsourced from public vehicles. I have listed some links here for some of the recent projects in this regard. There is the most prominent one is the Lyra project sponsored by the Danish government. But then you can see Naira Dynamics has made a lot of advances in this regard, and Virginia Tech did a study under NSF for similar concepts. University of Pretoria has been doing an initiative calling them in Engineering 4.0, where they're using a lot of Internet of Things technology. And University of Michigan did under USDOT a study, a safety pilot, where they were correlating the friction measurements that they are getting from standard testing equipment to connected vehicles. Natural language processing has been used a lot in construction industry for compliance checking from regulatory documents or for requirements extraction from construction contracts. There are links here. You can see the research that is ongoing on this in this area. Another example could be if you wanted to detect and extract written construction history. If you have a lot of documents about the construction history, but you don't have a numerical database of certain values that you are looking for, you can do like a question and answer mechanism with the natural language processing technology. For example, you can ask, what is the depth to bedrock at milepost 202 on highway US 1, maybe, as an example, and you're looking for the answer to this question. You can form this as an open book problem where you give the digitized documents to your algorithm. The algorithm will have two steps. One is the retriever, which is basically selecting which documents are most relevant to this problem based on certain criteria. And then you will have a reader where you will use a fine-tuned language model. And language models have been in development. These are all emerging. BERT is one by Google. OpenAI has this GPT-3, and there's like an open source version of it called GPT-J, which everyone can use. And then NVIDIA and Microsoft came up with the largest pre-trained language model ever. And then, of course, you need to fine-tune these language models to your specific problem. For example, here in this construction history, you need to create some kind of synthetic database to be able to fine-tune your model. Now, about emerging technology for data analysis and data-driven decisions. Again, there's been a lot of research ongoing for integration of disparate data sources with each other, where artificial intelligence is being used, or machine learning for detection of unrecorded maintenance. I'm going to talk a little bit about distributed AI and continuous learning applications. Distributed AI is basically where you are using the same concept, just like as in big data, where you are distributing your data over these computing nodes over the cloud, or the computing nodes over a network of connected instruments. And basically you are trying to conduct your training of, let's say you have a machine learning algorithm over these distributed networks of computing nodes. There are two ways of doing this. One is data parallelism, and the other one is model parallelism. So data parallelism, which is the most common and the easier one, is in which where you copy parts of your training data, because your training data is huge. Let's say it's coming from connected vehicles. you are dividing this training database into multiple sets, and then you are giving each set to one of the computing nodes. Here in this illustration is trying to show this concept. So each one of the computing nodes takes a part of the training data set. And then you are assigning each one of these computing nodes to optimize the parameters in one layer of your model. So if you're familiar with machine learning models, especially deep learning models, they have many, many layers, and the parameters in each layer needs to be optimized for your training to be effective. So in this data parallelism, basically you are asking each one of these compute nodes to optimize one layer, the parameters in one layer based on the data that is delivered to that compute node. In model parallelism, your model is so huge that you can't copy your model into each and every one of these compute nodes. And that is a rare case. I would say maybe, Microsoft, NVIDIA, or Google, when they were trying to come up with their pre-trained language model, which is like a huge NLP model, that's where they would use a concept like model parallelism. So of course, the main objective here of distributed AI is accelerating the training on the cloud when your data is huge. But another application that could also be used in transportation infrastructure is to train models near the data source. This is especially applicable when you have edge devices. Edge devices are basically these computing devices that can be deployed in the field near the data source. Let's say, for example, at an intersection, you have a traffic camera, and you can basically equip that traffic camera with the edge computing device. What will happen is that you can train one layer of your deep learning model on the images that are coming from that camera using that edge device that you have deployed in the field. This way, you will optimize the use of your limited bandwidth in your network of communication. So you will not transfer all the data over that limited bandwidth. You will only transfer the intelligence that you have learned from that data. Again, there's a lot of research ongoing on this. We will have to see how much of it will actually make it to practice, especially in transportation. Another concept that I want to talk about is continuous learning. Again, we see a lot of this ongoing. This is where the models self-train with newer real-time sensor data. Basically, the model learns new observations while at the same time working on older predictions. So this concept can also do a continuous comparison against better performing models. Better performing models could be the models that you have developed in the past with older data, or it could be models that your peers have developed. And you can also cross-train based on different data. So basically, if your peers provide the parameters of their deep learning model with you, if they share it with you, you guys can learn from each other. Basically, this continuous learning concept is in a way that providing a sharing mechanism between different researchers. The application, of course, in performance prediction is very obvious. We can augment standardized data sources, like with these multi-purpose survey vehicles that we are using right now. We can augment it with crowdsourced data using this continuous learning method. We can also update our models more frequently. Instead of an agency updating their performance prediction models once every 5 years or 10 years, they can update it every day based on this stream of big data that is arriving every day. Which, of course, it will provide a more robust prediction for future conditions for asset management. Of course, it is also applicable in online predictions for maintenance management. So I talked very fast about these emerging technology research. I have provided some links here, just like Matt provided some links. I'm not really going to go through this. I'm hoping that after the conference, you can download the PDF of this presentation and you can get some information about these. Now I'm going to talk a little bit about technology transfer. Again, I'm not going to read through this slide. These are some of the most important, or the ones that I am aware of in terms of technology transfer in transportation. There are, of course, other avenues, but you can see that Federal Highway has several programs depending on where your technology is in terms of market readiness. And then There is, of course, small business innovation research and small business technology transfer projects. Our company, Callentis, is working on similar projects like this for Department of Transportation and Department of Energy. So we are basically conducting some of this technology transfer there. But Federal Highway has other programs, and CHRP has the IDEA program. And of course, last but not least, is this conference is organized by the University Transportation Center program, which the USDOT has, and they have some technology transfer initiatives. Now, the concept that I really wanted to talk about is the technology readiness levels, which was first adopted by NASA, but then Federal Highway came up with a TRL guidebook in 2012, which is basically dividing these various steps of technology transfer into these four prominent overarching steps. You start with your basic research, data evaluation, application formulation, then you move to applied research, which is supposed to create like a proof of concept. And this is where you will see a lot of doctoral dissertations stop, which is at the end of the applied research. And then you want to move to development, where you actually do a lot of validation and verification. And then after the development project is done, these development projects, examples of which would be a lot of government-sponsored research projects. Then that is actually when another huge stage starts, which is implementation, which requires industry outreach, standardization, commercialization, which can take a lot of time. One of the concepts that can help with technology transfer is customized no-code data science portals. There are off-the-shelf tools that are no-code data science portals, but these are not customized for specific problems like the problems that we face in transportation industry. Having it customized will allow us to reconcile data science with transportation engineering. It will be like a learning by doing or active learning paradigm in which you can train your current staff and future staff, like students, in data science, while simultaneously enabling them to explore and discover trends in the agency data. You can use data visualization to illustrate concepts, the statistical concepts in data science, and at the same time, you can also find and address data issues that you find in the data. Again, with the commercial off-the-shelf tools, you can't really do this because transportation engineers are the people who understand the source of the data, how was the data collected, so they can pinpoint what are the data issues using these statistical tools. Application programming interfaces, or APIs, are very powerful in these tools because they allow for running available open source packages of data science, so you don't have to reinvent the wheel. And also they are very useful for integrating the results that are coming out of these portals into existing software. Agencies have existing asset management software, and of course they don't want to change that huge implementation, but they can use the output of these data science portals in those software very simply by just an API. Another concept that is very important in technology transfer or operationalization of machine learning is what people call MLOps these days. It's a huge word these days. Basically, it is trying to handle the machine learning issues like data quality, like model decay. Model decay is very important because as you are collecting more new data, your old database that you use for training basically becomes outdated and you have to train on more new data. So that is why this machine learning operations concept was created. You can see some examples by NVIDIA and Microsoft, basically trying to oversee the machine learning lifecycle. What happens after you train your model, after you validate your model? You need to deploy your model. You need to continuously monitor the performance of your model. How is your machine learning model doing with new data that has not seen before or from different applications? What is the generalization capability of it? And then you continuously retrain your model. I'm going to wrap it up here by saying that, of course, research is ahead of the industry practice, especially continuous data generation is really requiring continuous analysis. And we need to learn more from other fields of practice. For example, asset management can learn from transportation systems management and operations. And we can also, with these new technologies, with transfer learning, we can share more insight across our industry, different researchers in our industry. And of course, I talked a little bit about technology transfer, but that's a whole new world. I mean, that's a whole separate world where you have to do a lot of benchmarking, calibration, validation, verification in order to be able to standardize a new technology. And for that purpose, the technology readiness levels is a very good framework that provides a systematic approach for technology transfer. If any of you have an idea that you think is practice ready, I'm all ears and would like to discuss that. That's where I will stop my presentation, Salah.